We will talk about the 6th lecture on module 2 in the online course on risk and reliability of offshore structures. In this lecture, we will continue with the reliability methods which we started in the last lecture. This is the lecture on module 2 on the online course on risk and reliability of offshore structures. We are talking about the focus on reliability theory and structural reliability in module 2. We already said as a part of the design process, we generally introduce safety check measures, okay, as a part of the design process. Which is considered to be one of the levels of reliability. Is level 1. We introduce method of safety checks, which is actually level 1 of reliability. But unfortunately, or more interestingly, even the method of safety checks also could introduce uncertainties. Let us see that slightly later, but now let us make a statement that human error, which is one of the main of most of the accidents, and mishaps, is not included in arriving at these safety checks. So, they still remain as one of the important source of uncertainty. Okay, that is very important. Now, how to avoid this or how to improve on this? One can work on improving inadequacy in knowledge, inadequate training, inadequate experience. So, one has to work on this to really comply the standards of safety practices to all personnel involved in offshore industry. So, this could be one of the improvement techniques. To improvise safety or to improve safety, which will address partly the errors occurring from or uncertainties occurring from human errors. Now, let us come back to this first statement. We said that method of safety or checking of safety may also introduce uncertainty. We can take a very classical example. Let us say we check the joint adequacy, what we call joint adequacy checks, based on empirical rules. Of course, one can argue that these empirical relationships are based or derived from model tests, no doubt on that. I will show you later in this module one of an application study what we did, where the inferences derived from the model test for stress concentration factor, the load carrying capacity of tubular joints, maybe K, L, T, etc., show a different significance compared to the top which has been derived based on the so called empirical studies which are referred back in the literature. So, even then this will lead to lot of uncertainties. Okay. So, one method by which this can be improved upon is updated research. So, this has been updated continuously. I can give a classical example on this. Let us say, for example, about 90% of the joints have fatigue life in excess of 1000 years. So, once the statement is realized and understood, then one can say that the so called SN curve is a very conservative estimate. Which has a very substantial reserve in estimating the fatigue life. The other way by which uncertainties arising from the checking process can also be overcome by doing periodic underwater inspection, which can address some issues related to critical joints, at least on critical joints, because this will be helpful in arresting the crack propagation. So, having said this, let us come back to the formulation of reliability problem. Let us recollect the reliability problem is nothing but identifying a limit state function, then integrating this function in the preferred domain to really find out what is the value of this function, whether it is positive or negative, to know whether it is going to be safe or unsafe. So, reliability analysis of offshore structures could be actually formulated in different ways. This formulation broadly can be grouped into two. One is what is called time invariant problem, the other is time variant problem. That is the overall broad grouping of reliability problems as applied to offshore structures. What is the commonness between these two? We will see them independently, but let us quickly see the commonness between these two. In both, a limit state function should be defined. That is common. This function of course should be based on either limit state of serviceability or ultimate stress criteria. So, one has got to prefix this before we do a failure analysis or probability of failure of any specific function, not the structure. So, the limit state function or the probability of failure of this particular function or probability of this function falling in the failure domain can be assessed when one of these prerequisite is available and applicable to the problem of our interest. Therefore, reliability problem aims to determine the probability of limit state failure. So, the aim of reliability problem is to determine the probability of limit state failure which violates the limit state condition. The assumed limit state condition. Now, for time variant problem, let g of x indicate the limit state function in which x denotes a set of random variable probability of failure is given by probability of this limit state function assuming a value less than 0, which is alternatively integration of the probability density function over the domain D. So, let me call this equation number 1. In equation 1, the joint probability density function and the integration is performed over the domain D. Okay. F of x is the joint probability density function which is whose integration is performed over the domain D. Okay. Once you know the probability of failure, reliability is nothing but 1 minus probability of failure, which is converse of the probability of failure. Okay. So, reliability can be estimated. I request you to please look at the screen now. The screen shows a graph between two variables x1 and x2, which is indicating conceptually the reliability with two random variables x1 and x2. Therefore, the plot shows the limit state function indicating or connecting x1 and x2. For example, for our understanding, x1 can be the loads and x2 can be the material strength. Okay. So, let us pick up two random variables whose connectivity is to be established by a limit state function. Let that be g of x as indicated in the blackboard here. So, g of x1 x2 should be equal to 0 is a limit state function. If it is exceeding 0, which is shown in the hatched position, it is a safe domain. If g of x is less than or equal to 0, which is shown here, it is a failure domain. So, this becomes a simple illustration graphically which shows me the concept of reliability with two random variables x1 and x2. Having said this, integration of a suitable or appropriate probability density function within the shaded area is a reliability against failure. So, g of x1, x2 and so on, x1 and x2. So, this is my shaded area where g of x is greater than 0. This is the area where g of x is less than or equal to 0, which is the failure domain. So, integration of a suitable probability density function within the shaded area is actually the reliability, because that is the safe area. Okay. This is the failure area, 1 minus failure is going to be the safe area, right. Therefore, reliability analysis amounts to integration of a suitable probability density function within the shaded area A reliability problem is therefore said to be time variant if the following statement is valid. Let us say time variant problem. In this case, obviously the limit state function is also going to be a function of time. Function of time. In more specific terms, limit state function will be defined by a specific set in which the variable x is going to represent set of random variables and y of t, let us say, is going to represent a vector of stochastic process. So, I can say the limit state function for a time variant problem can be expressed as g of x comma y of t. The failure event of such problems may constitute the outcrossing of the vector processes y of t through the limit state surface g of x y. So, essentially the failure event means in this case is actually the outcrossing of the vector y of t through the limit state surface. Which is simply g x y 0. So, let us see how this function looks like. I request you to please look at the screen, which is a graphical illustration of the time variant reliability problem. There are two variables, let us say y1 and y2. G of x y is equal to 0 is what we have the limit state function chosen for this problem. The shaded one indicates the outcrossing failure surface, as indicated here, and y of t is actually a vector which outcrosses this limit state function when it processes through the value. So, the probability of failure in this case is given by, so probability of failure is going to be limit integral of the value of t between 0 and t. We have to set up, because I already said failure is defined as non-performance of a function over a specific period of time under specific conditions, is it not? So, time has got to be also specified. Why time is not important in the earlier case equation? Because the limit state function chosen remained to be time invariant, whereas in this case, since the limit state function is going to be representing the time variant problem as well, therefore, time boundary will also come into play here. So, probability of minimum g of x y t less than or equal to 0 given x given f of x dx. Equation number 2. In equation 2, T actually denotes, the capital T denotes the lifetime of the structure. And small t denotes the instantaneous of time, or let us say f of x is the joint probability density function of x. The conditional probability is defined by the terms within the parenthesis, which is obtained by the stochastic analysis of the structure for random loading y of t. Now, there is a problem with this equation too. The exact solution of equation 2 to determine the outcrossing analysis is difficult. Why? Because there are two reasons for this, because of two reasons. The first reason could be evaluation of conditional probability and second could be determination of joint probability density function itself. In fact, determining the joint probability density function is also one of the reasons for not being able to obtain the exact integration of the equation 2. So, the failure domain of this is what you see in the screen now, which has been also shown to you earlier. That is the failure domain, which you see for a time variant reliability problem. Having said this, let us revisit back the reliability methods in the focus of time variant and time invariant problems, or in addition to that in the focus of uncertainties arising from various sector as discussed earlier. So, let us talk about reliability method again, but with a different perspective this time. There are many reliability methods, or there are many methods of finding probability of failure of structures involving the functions of random variables. Accuracy of all these methods depend on two critical issues. So, one can choose any method to determine the probability of failure, but accuracy of obtaining probability of failure depends on one, how accurately the joint probability distribution functions of random variables are determined. That is first. Second could be how accurately the integration of the limit state function over the failure domain can be evaluated. So, two critical factors will govern the accuracy of the method, which is a reliability method. In addition, based on the methods of estimate of joint probability distribution functions, they can also be classified either as analytical or numerical. So, one can even say analytical method or numerical method of reliability based on the pattern or based on the method by which we are estimating the joint probability density function. So, one of such methods is very commonly applied in the offshore industry is first order moment method. Let us say FO SM. In this method, a first order Taylor series approximation of the limit state function is used. And hence the name first order. Only second moment of statistics of the random variables are used. To obtain the probability of failure. That is why the method is called first order second moment. So, first order approximation, second moment, therefore, first order second moment method. If two random variables are used to derive this method, the limit state function for two random variables R and S, okay, is given by Z is equal to R minus S. Assuming that R and S are statistically independent, if they are normally distributed, then Z is also normally distributed. Therefore, mean of Z can be said as mean of R minus mean of S. Variance can be said as variance of R, variance of Z. Now, the probability of failure is given by probability of Z taking negative value, that is probability of now, as we said earlier, if Z is a normal variate, if we assume that R and S are normally distributed, then Z will also be normally distributed. Then in that case, probability of failure can be easily given by a closed form solution, which is going to be the phi function of minus mu Z by sigma Z, where phi is a cumulative distribution function, of the standard normal variable. Now, substituting for mu z and sigma z, because we need this in equation 7, we get probability of failure is 1 minus phi of mu r minus mu s by sigma square sigma s. Equation number 8. Now, in this equation, the ratio of mu z by sigma z is called as reliability index, indicated by beta, which is otherwise called as safety index also. In that case, probability of failure is then given by phi of minus beta let us say if the variables are log normally distributed, then the limit state function is given by z of r by s, where z is the normal variable and probability of failure is given by 1 minus phi of ln of mu r by mu s root of 1 plus divided by root of ln of this is not sigma, they are deltas. Please make a change here, deltas, where delta r, delta s are coefficient of variations of r and s. Now, the above formulation may generate and can be even generalized to any random variables, because we have taken here two random variables r and s, can generalize it for n number of random variables denoted by a vector x. In that case, the performance function can be simply g of x. So, the Taylor series expansion of the performance function about the mean values can be given, which can be studied for FOSM, which we will see in the next lecture. Friends, I hope you understand. In this lecture, we have covered the important aspects of reliability methods. What are the constraints which govern the accuracy of the reliability method? How the choice of probability density function can also lead to accounting various uncertainties at different levels in the analysis. We started with different methods of reliability. We started with the first method, which is first order second moment method. We took two cases. One is if the variables are normally distributed, if the variables are log normally distributed, how can you estimate the performance a function and how can you find out the probability of failure of this function using these two normal variates or log normal variates. We will continue with this in the next lecture. Thank you very much.